In this tutorial, we're going to go through a few examples from Chapter 5, Linear Elastic Materials Constitutive Equations. The first problem, you're given a state of strain inside a continuum represented by the small strain matrix given here, and assuming that the material is steel with Young's modulus of 210 gigapascal and Poisson's ratio of 0.3, it also follows the von Mises yield criterion with sigma max equal to 750 MPa. We need to find the principal strains. After finding the principal strains, we also need to find the principal strains directions, which basically the eigensystem of the strain matrix. Then we need to find the principal stresses and their directions. To find the stresses, we need to use the constitutive law to replace the strains, or to multiply a big matrix by the strains to get the stresses. Then after getting the stresses, we need to find the principal stresses and their directions. And then after finding the stress matrix, we can evaluate the von Mises stress and compare it with the 750 MPa. So the first step involves writing the strain matrix. So I'm going to call the strain matrix STR. A matrix is input as in between a set of curly brackets. Each row is another set of curly brackets, so I have 3 rows. I'm going to input the values 0.002, 0.001, 0.002, and so on. I'm inputting each row in a set, inside a set of curly brackets. To find the principal strains and their direction, I can input these principal strains and those principal directions inside the variable A. This variable A is made out of the eigensystem of the strain matrix. I'm going to present the strain in matrix form, and I'm going to present its eigensystem in matrix form. Notice I'm writing everything in the same cell. Shift enter, and here is the answer. This is the matrix that I input. I just want to make sure that I use the correct numbers. True. And the eigensystem is made out of 3 eigenvalues and the corresponding eigenvectors. This is the first eigenvalue, the second eigenvalue, third eigenvalue, first eigenvector, second eigenvector, and third eigenvector. In order to find the stresses, I have to utilize the constitutive relationship between the stress and strain, which in the book is given as a relationship between a vector representation of the strain and a vector representation of the stress. Now, we understand that the stress and the strain are matrices, but to relate the two, we're going to use a vector representation. And this vector representation for the strain, I'm going to call it the strain vector. The strain vector is a vector made out of certain components of the strain. The first component is epsilon 1, the second component is epsilon 2, the third component is epsilon 3, and then epsilon 1, 2, epsilon 2, 3, epsilon 1, 2, epsilon 1, 3, and finally epsilon 2, 3. So this is my strain vector. You can view the strain vector in matrix form. Shift enter, and here's my strain vector. Now, actually in the strain vector we utilize the shear, or the engineering shear strain, which is equal to 2 multiplied by the entries in your strain matrix. So don't forget this 2, otherwise your numbers, or the stress numbers, will not be correct. Shift enter, and here's This is epsilon 1 1, epsilon 2 2, epsilon 3 3, 2 epsilon 1 2, 2 epsilon 1 3, 2 epsilon 2 3. The relationship between the stress and strain is defined using a big matrix. I'm going to call this matrix CC. This big matrix is a 6 by 6 matrix. So it has 6 rows. 1 2 3 4 5 6. Each row has Young's modulus and the shear modulus and Poisson's ratio. The entries are functions of Young's modulus, which I'm going to call EE. EE is given as 2 1 0 1 2 3 MPa, and Poisson's ratio is given as 0.3, and I'm going to utilize Poisson's ratio and Young's modulus to calculate G, which is equal to E divided by 2 divided by 1 plus Poisson's ratio. I'm going to just make sure that my calculation for G is correct. Shift enter. Indeed, this is my G. The relationship is made between the stress and the strain is given by a matrix, a huge matrix that's 6 by 6. The entries of this matrix are as follows: 1 over Young's modulus, negative Poisson's ratio over Young's modulus, and notice that Mathematica is case sensitive, so I'm using capital nu, then I'm here using capital nu as well, negative nu over EE, and then a bunch of zeros. The second row is equal to negative nu over Poisson's ratio over E, 1 over E, negative nu over E, and then a bunch of zeros. The third row is negative Poisson's ratio over E, negative Poisson's ratio over E, 1 over E, and then a bunch of zeros, and then 1 over G, and then 2 zeros, a bunch of zeros, and then 1 over G, and then a 0, a bunch of zeros, and then 1 over G. I'm going to show C in matrix form just to verify that my input is correct. Shift enter. 1 over E, Poisson's ratio over E, Poisson's ratio over E. So this looks correct. This is my matrix C. Now the matrix C relates the strains to the stresses. In fact, the strain vector is actually equal to C multiplied by the stress vector. But what we're interested in is the stress vector. So I need to find the inverse of C. So I'm going to get a matrix D, which I will get by inverting the matrix C. Then let's see matrix D in matrix form. Here is the matrix C and here is the matrix D. To find the stresses, the stress vector is equal to the matrix D multiplied by the strain vector and notice that I'm using the dot to multiply the matrix by a vector. Shift enter, and here's my stress vector. This is sigma 1 1, sigma 2 2, sigma 3 3, 1 2, 1 3, 2 3. To find the principal stresses, I need to form my stress matrix. So the stress matrix will be equal to a 3 by 3 matrix. So I'm going to use a set of curly brackets, and I will take the appropriate values. So this is the first entry in the stress vector. This will be the entry number 4 in the stress vector. Notice that to extract a value from the vector, I need 2 sets of square brackets. This will be stress vector, the entry number 5. So this is sigma on 1, sigma on 2, sigma on 3. It's symmetric, so I'm going to use stress vector 4, then sigma 2, 2, and then sigma 2, 3. I'm going to show the stress matrix in matrix form just to verify that this is true. So sigma on 1, I put it here. Sigma 2, 2, I put it here. Sigma 3, 3, I put it here. Sigma on 2, I put it here and here. Sigma 1, 3, I put it in here and in here. And sigma 2, 3, I put it in here and in here. So it's correct. Now the eigensystem of the stress matrix, let's put it in a list called V, and we can view V in matrix form. I'm going to put here a semicolon just to suppress the first output, and then view V in matrix form. Shift enter the first eigenvalue, the second eigenvalue, the third eigenvalue, and the corresponding eigenvectors. Finally, we need to calculate the von Mises stress for this stress state. Now I have here the function that calculates the von Mises stress from a stress matrix, which I created in a previous assignment. So I'm going to paste it here. This is the von Mises of a certain matrix is equal to a function of the entries of this matrix. So I can say now the von Mises, find the von Mises of the stress matrix, shift enter, and the von Mises of the stress matrix is 1031.19 MPa, which is much bigger than sigma max, indicating that this stress state or the strain state is not possible before yielding of the material. Alright, in the next problem, first I'm going to start from scratch, so I'm going to quit all quit the kernel, so I'm starting from scratch. No variables are stored in the Mathematica kernel now, and I have the position function in dimensions of meter of a plate follows the following form. x1 is a function of capital X1, the second component x2 is function of the original capital X2, and x3 is function of capital X3. The plate has dimensions of 2 meter and 1 meter in the direction of E2. We know we should need to show first that this is a state of plane strain. So to show that this is a state of plane strain, first I need to find the strain matrix. So I'm going to write the new position x is equal to x1, x2, x3. The old position x is equal to capital X1, capital X2, capital X3. I already am given the functions for small x1, which is equal to capital X1 plus 0.001 x2 plus, so I'm just copying the values from above, the functions given, and x3 is equal to x3, indicating that the plate has not moved in the third direction. U, the displacement vector, is equal to x minus x. I'm going to form, just going to show U in matrix form. Shift enter, and this is the displacement vector. To show that this is a state of plane strain, I need to calculate the strain. First, to calculate the strain, I need to calculate the matrix grad U, and the gradient of U is equal to a table made out of the partial derivatives of ui with respect to xj, where I is from 1 to 3 and j is from 1 to 3. And I'm going to show the gradient of U in matrix 4. Shift enter. Here is the gradient of U in matrix 4. This engineering strain matrix is equal to 1 over 2 multiplied by the gradient of U plus the transpose of the gradient of U, and shift enter. I should view it in matrix form, and here's the output. And you could see, indeed, it's a state of plane strain because I only have epsilon 1, 2, epsilon 2, 2, epsilon 1, 1, 2, 2, and epsilon 1, 2. The green strain is equal to half multiplied by the gradient of U plus the transpose of gradient of U plus the transpose of the gradient of U dot the gradient of U, the two matrices multiplied by each other. And green, I'm also going to view the green strain in matrix form. Shift enter, and here's green strain, and you can use the function full simplify to simplify the entries of the green strain. Okay, so here's we calculated the engineering small strain and the green strain matrix, and we need to show that the small strain is adequate to describe the motion. If you compare the numbers, let's full simplify the engineering strain as well. If we compare the numbers, this is the small strain and this is the green strain. This is 0, 0, and here 0.004x1, 0.004x1 plus 8 multiplied by 10 power negative 8 x1 squared. So this 8 multiplied by 10 power negative 8 is very small, so this can be ignored. And similarly here, 2 multiplied by 10 power negative 7 x1 is very small compared to 0.005, so it can be ignored. So basically, when you compare the numbers of the engineering strain and the green strain matrices, you can ignore the small numbers, and you can conclude that I can use the engineering small strain to describe the motion. The next step is we need to plot the vector plot of the displacement function. The displacement is given in vector as a vector in R3. However, the third component of the displacement is 0. So I would like to just use the two-dimensional version of the U, of the vector U. So I'm going to define a new vector called u2d, which is equal to the first two components of u. So this is the vector u2d just by taking the first two components of u. This is the first component, and this is the second component without the third component. And I would like to plot a vector plot of this u2d on my domain, which is the plate, and the plate has two dimensions in E1, so x1 goes from 0 to 2 and x2 goes from 0 to 1. Shift enter, and here's my two-dimensional the vector plot of my plate. Notice that the aspect ratio is not very good, because the plate has height of 1 and width of 2, and it just makes it into a square. So I'm going to add an option here, comma aspect ratio. I'm going to use automatic, shift enter, and I get the vector plot of the displacement in the plate. This tells me an indication of how the plate is moving in space. This point is moving in this direction with this vector. The points closer to the origin are not really moving. The points closer to this edge are moving horizontally, and the points closer to this edge are moving in the dimension of this vector. Afterwards, so after we've drawn all the displacements and everything, we're given Young's modulus and Poisson's ratio, and we'd like to find the equilibrium body forces to which this plate is subjected, and then we need to draw the contour plot of the von Mises stress and the out-of-plane stress component. Out-of-plane stress component, it's sigma 3,3. So Young's modulus is given as 210 gigapascal, so 210 123 MPa. Poisson's ratio is given as 0.3, and the shear modulus will be equal to E divided by 2 divided by 1 plus Poisson's ratio. I'm going to utilize the matrix that I defined in the previous problem. So I'm going to take this, copy, and go back, paste. So this is the matrix that relates the strains to the stresses. The strains are equal to this matrix CC multiplied by the stress. The inverse of this matrix relates the stress to the strain. So the stress vector is equal to this matrix DD, which is the inverse of C, multiplied by the strain vector. So first we need to define the strain vector. The strain is given as a matrix. Now the strain vector will be given as a vector representation of the strain, so I need to define it here. Strain vector, again I'm going to copy it from the previous problem. The strain vector is equal to the components of the strain matrix. Now I called the strain matrix here engineering strain, so I'm gonna put engineering strain instead of strain because this is this problem, and I'm going to show the stress vector in matrix form. Shift enter, and here's sigma 1 1, sigma 2 2, sigma 3 3, sigma 1 2, sigma 1 3, sigma 2 3. Now what the question is asking for is calculate the equilibrium body forces and draw the contour plot of the von Mises stress and the out of plane stress component. So first I'm going to draw those contour plots. So contour plot. Sigma 33 is the third component in the stress vector. Again, this is drawn for x1 from 0 to 2 and x2 from 0 to 1, and given aspect ratio automatic. Shift enter, and here's the contour plot, but I don't see any numbers, so I'm going to add the numbers here by saying contour labels all, shift enter, and this gives me the numbers, which means sigma 33 at this point is given by 80 MPa. At this point it's 100 MPa. At this point it's 140. Between this line and this line, it's between 120 and 140. So this gives me a measure of what the values of the stresses are throughout the plate. Right here, this is the maximum, the area of the highest stress in the plate, with a value of over 200 MPa. To calculate the von Mises stress, first I need to form the stress matrix. So the stress matrix will be given as, by taking the components of the stress vector, I can make the components of the stress matrix. So first component and so on, just similar to what we did in the previous problem. So this gives me the stress matrix, and again using the von Mises function that we defined in the previous problem, I can input this function here and then calculate the von Mises. Calculate the von Mises of the stress matrix. Let's put it after the contour plot. Shift enter, and here's the von Mises stress. Now you notice that it's a lot of I can simplify this this value simply by saying full simplify the stress matrix. Actually, full simplify the value, so full simplify whatever output is, shift enter, and here's the von Mises stress as a function of the components inside the plate, and I can plot these values in a contour plot. So I'm going to store this in a value called VM, and I'm going to draw the contour plot of this VM on the plate. Shift enter. So this is the value of the von Mises stress. The maximum von Mises stress is that this is closer to this location with a value of 210 MPa, which means if I'm designing this plate, the point that I have to look at or that I have to watch for is this area, because this is the maximum von Mises stress. And just for aesthetics reason, you can add a label. You can say this is plot label von Mises, shift enter, and it adds the label to your plot. So we've calculated Young's modulus, Poisson's we've calculated the contour plots, or we've drawn the contour plots of von Mises, the out of plane stress component, which is sigma 33. We need to find the equilibrium body forces, so similar to what we did in chapter 4. We already have the stress matrix. So this is our stress matrix. or the stress vector representing the stresses inside the plate. To calculate the equilibrium body forces, I need to take the derivatives of the different stress components with respect to x1 and x2 and x3. So this is the stress matrix. Rho B1 is equal to the following. So rho B1, the first component, I'm going to just call it B1, B2, and B3. When you look at your equilibrium equations, rho B1 and rho B2 and rho B3, they're equal to partial sigma 1, 1 plus partial x1. Partial sigma 1, 1 by partial x1 plus partial sigma 2, 1 by partial x2 plus partial sigma 3, 1 by partial x3. And this is what this sum function does. Takes partial si1 by partial xi when I goes from 1 to 3. Rho B2 is the same, but instead of partial sigma I1, it's partial sigma I2. And rho B3 is partial sigma I3 instead of partial sigma I2. But don't forget that for this particular problem, we're using stress matrix, not S. So the value is called the stress matrix. Shift enter, and here are the three values of the body forces.